The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust.
Remember that although the plates are riding on top of the mantle is a solid body of rock, not a liquid.
Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on, unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental land masses, the thinner of the two plates bends and slides under the other. As the edge of the seafloor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.